So now let's get back to chloroethane. Why are there so many peaks? If we think about this compared to the previous spectrum we looked at that had the two doublets, why so many peaks in chloroethane? Why is there a group of 4 and a group of 3? So we're going to call these HA, and these will be HB. So let's look at HA first. How many neighboring or how many adjacent hydrogens does HA have? HA has 2 neighboring hydrogens, HB. So let's consider what can happen. Well, those 2 neighboring hydrogens could both be aligned with the magnetic field. Both of those neighboring hydrogens could be aligned against the magnetic field. Or one of them can be with the magnetic field and one of them could be against the magnetic field. So overall, there's 4 possible scenarios that can occur for HA based on those neighboring hydrogens HB. Now, we're going to take these middle 2 and combine them. Why? Well, those 2 protons HB are the same. They're equivalent to each other. So it doesn't matter which one is with and which one is against. Those are overall the same situation. So what we're going to see for HA is we're going to see one peak where both of the neighboring hydrogens are aligned with the magnetic field. We're going to see one peak where both are aligned against the magnetic field. And we're going to see a third peak where one is with and one is against. But what we also want to note is that that situation is twice as likely to occur because there's 2 ways for that to occur, whereas the other situations can only occur in one way. So for HA, which is split by 2 neighboring hydrogens HB, it gets split into 3 peaks, which we will call triplet, and that triplet will be in a 1 to 2 to 1 ratio. Is that what we see in our spectrum? So again, we know that this is our HA, this is HB because of the electronegative chlorine, and you can see we have 3 peaks, 1, 2, 3, and they are in an approximately 1 to 2 to 1 ratio. Now, what about HB? HB has 3 adjacent hydrogens. So how many possible scenarios are there here? Well, all 3 can be with. We can have 2 with and 1 against. We can have 1 with and 2 against. And we can have all 3 against. So we have 8 possible situations. Now, which ones can we combine? Well, the first one where all 3 are with, there's only one way to do that. Same thing with this bottom method. There's also only one way to have all 3 against. But as long as our three protons HA are all equivalent to each other, then any situation where two are with and one are against will be equivalent. So that's these three situations. And there's three of those. There's also three situations where one is with and two are against. So what we end up with, I'm just going to put this last group in a different color so we don't think that they're the same. But we end up with 4 peaks, which here we call a quartet, in a 1 to 3 to 3 to 1 ratio. And that's what we saw in our spectrum, 4 peaks in an approximately 1 to 3 to 3 to 1 ratio. Now, it's possible to have more than 3 adjacent hydrogens. For example, if you think about an isopropyl group, this hydrogen here is now adjacent to 6 hydrogens that are equal. So who wants to start setting up a chart with all those arrows for 6 different hydrogens? You know, that doesn't necessarily seem like a lot of fun. That would be a ton of arrows that we've got to set up. So is there an easier way to predict this? Well, let's look at the following. So over here, number of adjacent hydrogens. We'll talk about the number of peaks. And then what are the ratio of those peaks? And we'll see if we can more easily make predictions. So if we have no adjacent hydrogens, that gives us just 1 peak, or what we call a singlet. And it's hard to talk about a ratio to itself, so we'll just say the ratio is 1. Now the next line that goes here is if we have 1 adjacent hydrogen. We've already seen that one before. If we have 1 adjacent hydrogen, then we have 2 peaks, or a doublet, and we saw that has a 1 to 1 ratio. The next two we've just done, 2 adjacent hydrogens gave us 3 peaks, or a triplet. Their ratio was 1 to 2 to 1. Three adjacent hydrogens gives us 4 peaks, or a quartet, and we saw that had a ratio of 1 to 3 to 3 to 1. So here's our first new one that we're going to try and predict. What if we have 4 adjacent hydrogens? So the first thing you should notice here is that the number of peaks is 1 greater than the number of adjacent hydrogens. So when we had no adjacent hydrogens, we got 1 peak. 1 adjacent hydrogens, 2 peaks. 2 adjacent hydrogens, 3 peaks, and so on. So you might predict at this point that if we have 4 adjacent hydrogens, that would give us 5 peaks, or a quintet. their ratio? 1 to 4 to 6 to 4 to 1. Where did that ratio come from? Well, you may have recognized this. This is one of those things that you probably saw in a math class a long time ago and wondered what the purpose of it was. But this is, of course, Pascal's triangle. And so we can keep going. 5 adjacent hydrogens gives us 6 peaks, or a sextet. 1 to 5 to 10 to 10 to 5 to 1. And we'll do one more row. If we have 6 adjacent hydrogens, that's what we see if we have an isopropyl group. We get 7 peaks, or a septet, with a ratio of 1 to 6 to 15 to 20 to 15 to 6 to 1. So those steps that we went through of drawing the arrows, of aligning with the magnetic field, aligning against the magnetic field, that's not something that we need to do each time. And we just need to go to the relevant row of Pascal's triangle, and that'll tell us what our splitting pattern is. All right, so those are our simple situations. What happens when our molecule starts to get more complicated? Or sometimes simplifying the molecule makes it more complicated. So here's cyclohexane. What do we think this will look like? Now we know all of the hydrogens are equivalent. We've talked about this example previously. But what would be the splitting pattern of one of these hydrogens? How many hydrogens are adjacent? Well, the important point here is if 2 protons are chemically equivalent, they don't split each other. So these 2 hydrogens that I've drawn in here, are they adjacent to each other? The answer is yes. Are they equivalent to each other? The answer to that is also yes. And so because they're equivalent to each other, they don't split each other. And so in the case of a molecule such as cyclohexane, all of the hydrogens are equivalent to each other. Because they're all equivalent to each other, there's no splitting at all. And so as you can see from the spectrum here, cyclohexane gives us 1 peak, and it's a singlet. Now, what if the hydrogens that are adjacent to each other are not equivalent to each other? What do we mean by that? So let's look at this proton that I have labeled in red. How many protons are adjacent to it? Well, we have 1 proton on this side, HA, and that's adjacent. Remember we talked about our 3-bond rule for determining that. On the other side, we have 3 hydrogens, which we're going to call HB. So our hydrogen that we're looking at here, it's adjacent to 4 other hydrogens, but it's not going to be a quintet. Why not? The reason it's not is because HA is not equal to HB. So what do we have to do? So first we're going to have to account for the splitting by HA. The splitting from HA would be a doublet because there's one adjacent hydrogen. But then this hydrogen is also split by these three HB. There's three HB protons. That would give us a quartet. So which one do we get? Do we get a doublet or do we get a quartet? Well, let's look at the actual spectrum. And you can see the actual peak here for that proton. So what did we get? We got both. And what's actually happening here is what we have is a doublet that got split into two quartets. Or in other words, you get a combination of these two splitting patterns, which could be a doublet of quartets or a quartet of doublets. How many peaks is that? Well, 2 from the doublet times 4 from the quartet is a total of 8 peaks. Would you be able to predict if it's a doublet of quartets or a quartet of doublets? In general, no. That's something that's fairly complicated to predict and not something I will expect you to do in this course. But once we start to have multiple types of hydrogens that are adjacent, the splitting patterns become more complicated. All right, the final thing I want to discuss in this area of splitting patterns is to talk about what about atoms other than carbon. So if we have an OH, an alcohol, first of all, does an OH proton show up in an NMR spectrum? The answer is yes. Protons on atoms other than carbon will still show up in an NMR spectrum. What about the splitting, though? In fact, I'm going to make these chlorines so that they don't affect the splitting at all. So if we're talking about this hydrogen right here, will it still get split by this adjacent hydrogen? Now, if it does get split, we know it's going to be 1 plus 1 or a doublet. So the answer to the question of will it get split is maybe. I know, terrible answer to give. But it turns out it's something you can't predict, especially not easily. And sometimes you can't, sometimes it might change depending on how you make up your sample. And this is a story that illustrates that. So when I was in grad school, if you want to publish a paper, on your research in organic chemistry, one of the things you have to do is, in addition to writing the paper, you have to write what are called experimental sections. And we've done a little bit of that in lab so far. But when you really get into research, those experimental sections become a lot more complicated. One of the things you have to include in there is a write-up of your NMR and IR and mass spec data. And the way that you do that is you would write something like, the chemical shift for each peak 3.14, and then you might give the splitting pattern D for doublet, and then you'd say it represents 3 hydrogens. How you know that is actually the next topic that we'll get to. That'll actually be the next topic after we finish splitting patterns. But what happened was I had a compound that looked like this. And so you can see that this hydrogen is next to this hydrogen and next to the OH hydrogen. And so this hydrogen can be split here and here. Since those two hydrogens are not equivalent to each other, each one will make it a doublet, and my spectrum showed up with that hydrogen being a doublet of doublets. And again, if I label these as HA, B, C, and D, what we were seeing was that HA got split by HB. That gave us 1 plus 1 for a doublet. And it got split by HC, 1 plus 1 for a doublet. Well, in a lot of cases, protons that are on atoms like oxygen don't show any splitting. And so I gave these experimentals to my advisor to read over, and he sees how I've cited these, and he's not happy, and he wrote this long note on there, do you understand splitting? And it went on from there. It wasn't terribly nice, and then finally he must have taken a second look at the data and realized that in this fairly unusual situation, I was seeing very nice splitting through oxygen. And so everything's crossed out and said, sorry, this is okay. And so the whole reason I bring up this story is, in answer to what I brought up is, do we see splitting through oxygen? The answer is sometimes. And so if you were taking a quiz or an exam in this course, and I gave you this example, and I said, what's the splitting pattern of HA? If you said that it was a doublet because this OH proton is adjacent, and we know it's adjacent because it's 1, 2, 3 bonds away. So if you said that it was a doublet, that would be correct. At the same time, if you told me it was a singlet because we don't see splitting through oxygen, that would also be correct, and you could justify that answer. So from here, you should go ahead and get out in-class exercise number 12, which will give you some practice at determining splitting patterns for hydrogens. And then we'll come back and pick up the last 2 topics for proton NMR, and then get into some practice of interpreting full spectra.